at the Turbo Machinery Laboratory of the Swiss Federal Institute of Technology, ETH Zurich. Unstable flow conditions occurring in centrifugal compressors have been investigated. For the visualization of rotating stall, a water model of a centrifugal compressor has been built. Centrifugal compressors are used, for example, in the engine of the Alouette 2 helicopter. The centrifugal compressor is the core element of the helicopter engine. This engine runs at the Turbo Machinery Laboratory of the ETH for educational purposes. The same gas turbine engine is to be found in the Alouette helicopter of Rega, the Swiss Air Rescue Guard. The gas turbine engine of such helicopters must operate reliably, even under extreme flight conditions in the Swiss Alps. Flow instabilities limit the compressor operation, and thus the whole engine operation, and influence the reliability of the engine. The engine components, shown in this model, are a one-stage centrifugal compressor, a combustion chamber, here the inner part, and a two-stage axial turbine. Detailed investigations of centrifugal compressor instabilities such as surge and rotating stall have been carried out at the Turbo Machinery Laboratory on a subsonic to transonic single-stage centrifugal compressor. To enable visualization of these unsteady flow phenomena, this air compressor has been modeled with water as the working medium. Compressor size and component geometry were kept unchanged. The incompressibility of water has been accounted for by a corrected shape of the blade height distribution. To achieve Reynolds similarity, the shaft speed was reduced to typically 3 to 5 revolutions per second. The dimensionless performance map of a compressor is a plot of pressure rise versus flow rate at constant shaft speed. The map shows the stage, the impeller, and the diffuser characteristics of the water model. Highest efficiency, the so-called best point, occurs at a flow coefficient equal to 0.072. Flow instability is encountered at or below a flow coefficient equal to 0.028. The performance map is a good criterion for the hydrodynamic equivalence of the air compressor and its water model. The comparison is made with the air compressor operating at a rim Mach number of 0.2. In particular, the comparison shows that there's an excellent match between the impeller characteristics of the water model and the air compressor. Rotating stall develops at the same flow coefficient equal to 0.028. Single-cell rotating stall occurs in both rigs. And the stall cell propagation speed is about 27% of the impeller speed in both rigs. With respect to rotating stall, one can conclude that the air compressor and the water model are hydrodynamically equivalent. The water model has been designed with a vertical axis. Its main components are the vertical suction pipe, the rotating impeller, and the annular diffuser surrounding the impeller and discharging the flow into an annular collector. The water flow is visualized by the injection of air bubbles. The following sequences show the plane view of diffuser flow under different operating conditions at a shaft speed of 3.3 revolutions per second. Next, transition from sound conditions to rotating stall is demonstrated. The through flow is gradually reduced from best point at 0.072 over the instability limit at 0.028 to 0.02 by closing the throttle valve. Sound flow with high turbulences is seen in all channels. At flow coefficient below 0.028, violently unsteady flow is seen to be established. In this sequence, diffuser channels are looked at through the annular collector during rotating stall operation at a flow coefficient equal to 0.02. Summing up the observations, the following conclusions can be drawn. The water stage is hydrodynamically equivalent to the air stage operating at a low Mach number. The water flow pattern shows full span single cell rotating stall. In the stall cell, the flow is stopped or locally reversed. Sound through flow continues to exist outside the rotating stall cell. Upon flow reversal, a trailing edge separation vortex is produced in each channel. Upon flow recovery, this vortex is swept away towards the discharge. During rotating stall, the diffuser channel flow is, in essence, two-dimensional. In order to prevent such pulsating flow phenomena from occurring in helicopter engines and other compressors, further questions have to be answered. Such questions are: what are the details of the impeller and diffuser flow structure? What's the nature of the instability that triggers rotating stall? What flow processes determine the propagation speed of the rotating stall cell? At the Turbomachinery Laboratory of the ETH Zurich, further research on the flow phenomena rotating stall will be carried out on the water model and the air compressor in order to answer these questions.